Welcome to this video lecture series of Basic Electronics, module number 1, lecture number 2, VI characteristics of PN junction diode, or we can also call it as a static VI characteristics of PN junction diode. Okay, so in our previous video lecture, we have just gone through how actually the basic PN junction diode will work under the forward bias and the reverse bias condition. Okay, and here the very first important thing is nothing but the semiconductor. Okay, the material which we are going to use in this PN junction diode is silicon material. Okay, now today we'll try to study how actually the VI characteristics of PN junction diode will be plotted, okay, along x and y axis, where V and I parameters are considered. Okay, so V represents the voltage and I represents the current. So if I change the value of voltage, okay, when we apply to the PN junction diode, okay, what will be the current ratings over here? Okay, so when you try to study the VI characteristics of a silicon diode, okay, we will not consider the Germanium diode. Okay, so in VI characteristics, okay, we will see how actually the diode will work under the forward bias condition and under the reverse bias condition. Okay, so before going to start with this VI characteristics, okay, let me show you the figure number 2, the forward and reverse characteristics of silicon diode. Okay, so this particular here, if I say that this is our quadrant 1, okay, let me take some 4 quadrants over here. Okay, so this is quadrant number 1, this is quadrant number 2, okay, this is quadrant number 3, and this is quadrant number 4. Okay, so there are total 4 quadrants are there in this particular VI characteristics. Okay, so quadrant 1 is for forward bias and quadrant number 3 is for reverse bias. Okay, so we will not consider any voltages or any value of current, okay, in quadrant number 2 and quadrant number 4. Okay, so this is how we try to plot the VI characteristics of a silicon diode. Okay, now if you look at this particular VI characteristics graph, okay, so this milliampere is with respect to the current which is plotted with across the voltage V. Okay, and this is our saturation voltage of silicon, which is 0.7. Okay, so if you look at this 0.7, we have a very sharp curve over here. So this particular sharp curve is our increase in the value of current at 0.2 voltages. Okay, so quadrant number 1, okay, and quadrant number 2, okay, sorry, quadrant number 1 and quadrant number 3, we are trying to consider. Okay, now there is a question which we can here we can go for is nothing but why we cannot consider the quadrant number 2 and quadrant number 4. Okay, if you look at the quadrant number 2 and quadrant number 4, the voltages, okay, we cannot apply the reverse voltages. Okay, can you just see here, right? So we have this the current over here is positive, but in quadrant number 2 the voltage is negative. Okay, so the property of a diode, or when the conduction will be only for the positive voltages, not the negative voltages. Okay, so therefore I cannot consider the quadrant number 2. Okay, because when you take a diode, okay, and you are trying to apply the positive voltage, not the negative voltage. Okay, so this is a positive voltage applied to the anode, okay, and the negative voltage is applied to cathode. Okay, so if you are trying to apply the positive to anode and negative to cathode, okay, so the flow of charges will be in this particular direction. Okay, so therefore when the this particular voltage is applied, so your diode will be working under the forward bias region. At what particular voltage? At 0.7 volt, because the material which we are using in this particular diode is silicon, that is nothing but Si, which is Si. So Si is equal to 0. That is why the reason, if you just look at here, okay, so if I try to increase the voltage from this particular region, that is 0, okay, so 0, 0.1, 0.2, 0.3, 4, 5, 6, slowly your voltage, so slowly your current will exponentially slowly it will increase. Okay, and at 0.7 we say that the diode is completely turned on. Okay, the diode is completely turned on. So this is what the characteristics of diode. Okay, so if you don't know the how actually the diode will work okay, then it becomes very difficult for us to design the circuit also. Why? Because if you are trying to feed the voltage 0.5 and 0.7, there is no conduction at all. Okay, no doubt your diode is turned on, but it will not conduct. It will only conduct at 0.7 voltage. Okay, so this is under forward bias in quadrant number 1. Now, if you take at the quadrant number 2, so what is happening in the quadrant number 2 is it is all the negative voltages. Okay, I cannot apply the negative voltage over here, because the negative, if I apply also, then your diode is completely reverse bias. Okay, then what happens? There is no conduction at all. Okay, because if I say that my diode is connected in this particular fashion, if I take quadrant number 2, okay, this is minus voltage and this is particularly the positive voltage. So if I say that if I'm applying the minus to anode and if I am applying plus to cathode, so what happens? This is completely off. This is completely off. It means that there is no flow of voltage or there is no flow of charge from anode to cathode, or if you can take that also cathode to anode. No voltage, and when there is no voltage, obviously there is no current, right? So therefore I will not get any kind of graph over here. So therefore my uh, 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 this quadrant number 2 is completely nil. Okay, similarly you can go for the quadrant number 4 also. You can check out with the quadrant number 4. But what is happening in the quadrant number 3? Okay, so if you look at the quadrant number 3, both the voltage and the currents are negative. Okay, both the voltage is also negative, current is also negative, but there is something which is happening in quadrant number 3. That is nothing but when you try to apply the reverse voltage over here. Okay, that is if I take this particular circuit diagram only. Okay, so minus is applied to anode and plus is applied to particularly cathode. Then what is happening here? Though you are there is no connectivity between from anode to cathode. Okay, then what is happening is as you are there is a small leakage current. Now there is another thing which is happening over here in this PN junction diode is, for example, if I say that this is my P material, okay, and this is my N type material. Okay, so if the P type material is connected to minus sign and the minus plus is connected to N type material. Now this particular line between P and N, we call it as junction. Okay, we call it as a junction. Okay, now what is happening to this particular junction is nothing but there are the positive charges over here, or you can say in terms of majority and the minority. So majority charge carriers will be over here, and the majority that is nothing but the holes, and the majority in the P type materials will be here, that is nothing but the electrons. Okay, so because the negative is connected to this P type and positive is connected to this particular N type, the depletion region, we call it as a depletion region. Okay, so the depletion region over here, when we connect in this particular quadrant where both the current and voltages are negative, it is it is very thick. It is become very thick in the sense we call it as the region between the P type and this particular N type, it will be very large. Okay, so any majority carriers over here or the minority carriers over, they try to just move from one region to another region like this. But what is happening, it is just like if you have a very thick wall, we can jump it very easily. If you have a very broad, or if I say that if the wall width is very too large, okay, then what happens, it becomes very difficult to jump, right? So therefore in quadrant number 3, as the voltage and the current both are negative, okay, it becomes the depletion regions will be very thick, and the flow of charge from P type to N type and N type to P type, it becomes very difficult. So therefore no amount of current or no amount of voltage will flow. But there is one current, we call it as a saturation, we call it as a reverse leakage current. Okay, we call it as a reverse leakage current, or a very small amount of current which is almost negligible current, or you can speak in terms of small only. Okay, the small leakage current will be flowing from this particular P type to N type material. So that is that we can see there is a sharp line, and at some amount of time it remains constant. It remains constant. So when it reaches to a point, okay, that point name is called as reverse breakdown voltage. Okay, or reverse saturation voltage point. Okay, so that particular voltage at which your current, small leakage current, will become very straight or sharp, we call it as a reverse breakdown voltage. Okay, now what happens is when you have applied this particular amount of voltage, that is minus to p type and plus to n type, and if you start to go on increase, just go on increasing, okay. For example, initially you have applied some 5 volt, okay, and you are moving towards in a increasing order. So when you reach at one particular point, that is called as a reverse breakdown voltage, and if you increase even a 0.001 volt or even a 0.1 volt, your diode will damage, okay, because all the materials has some capacity to withstand, okay. So we cannot just go beyond that particular voltage or such that we cannot, such that your diode becomes damaged, okay. So therefore here when we try to focus more on these particular regions, it becomes very difficult, okay. So therefore in quadrant number 3 it is not possible. Now when it comes to quadrant number 4, again the voltage is positive but the current is completely negative, okay, completely negative. So if I apply the forward voltage, okay, then also here you can see there is a sharp down, that is called as a reverse current, okay, which is going down. So that particular current, which will not allow to flow through that particularly PN junction, okay, because of the depletion region, which is very which is a bit thick. So that particular voltage is completely making our diode non-workable. So please remember, under the forward bias we work under the quadrant number 1, and under the reverse bias we work under the quadrant number 3, okay. So this is how the PN junction VI characteristics will work. So just look at this particular points where we focus is nothing but the forward current IF, okay, it remains very low until the diode is forward bias. So when the diode will be forward bias, it will be at 0.7. So after 0.7 it will go on increasing linearly, okay, and diode conducts as a much smaller reverse current IR when reverse bias. You can see here that is called as IR. So the IR will be very small, okay, reverse current is very small till it and when it reaches to some point it becomes constant, and after some points it will drop, okay, but you cannot go beyond that, okay. So when the diode is reverse bias, small current, that is IR, which is less than 100 nanoampere flows, okay, through a silicon diode until the PN junction breakdown voltage at a reverse voltage of about 75. So they have just taken an example over here, okay. So till minus 75 you can see a sharp constant line, okay. So at 75 it will stop. So if you go beyond 75 it will damage, okay. Now what is the problem here? They have just taken a problem here, okay. So this is how the characteristics of silicon diode is all about, okay. Now when you look at to the germanium diode, okay, you can just see here there is no much difference between silicon diode and germanium diode, okay. So at point, because the germanium has a rating that is 0.3 voltage, okay, so at 0.3 it will start turn on. So we cannot till 0.7, we will not wait for till 0.7. So at 0.3 it will start and it will be in the forward bias, and every other operation reverse remains same. Now the question here is, if the diode, if the voltage if we apply to any to a PN junction diode, okay, and that particular diode voltage is 0.5, okay, so whether still the diode is said to be in the forward bias, the answer is yes. The answer is yes. Your diode will be always in the forward bias until and unless, okay, until and unless if you do not change the polarity of your particular diode, okay. For example, just look at here, if your diode is in this particular fashion, okay, so and condition for the diode to be forward bias is that the positive voltage from a battery should be always applied to anode. You cannot change the polarity. So, and this is cathode, and minus should be always applied to cathode. So if this fashion or if this arrangement is maintained, then you say that your diode is forward bias, but you cannot say the diode is conducting, okay. If I say the diode is a silicon diode, okay, and if you have applied an voltage of 0.1 volt, whether still it is a forward bias, the answer is yes. The diode is forward bias, but the diode will not be in the conducting state because it has to reach, okay, because it has to reach 0.7. So if the condition is, if it is 0.7 voltage is less than 0.1 voltage is less than 0.7 voltage, then we cannot say that the diode will conduct. It will conduct, but the amount of voltage is too small. So if any voltage, okay, if I say any voltage, applied voltage, okay, any applied voltage, if it is greater than or equal to 0.7, yes, your diode is still a forward bias and it will conduct very properly. So we cannot allow, we cannot say that it will be say that the diode will be under a non-conducting state if it is less than 0.7. Okay, so this is how the diode will work. Okay, now the depletion region will break. Okay, so the diode will work or not? Yes, obviously the diode will work. That is what we are trying to do here. Okay, because you have applied the voltage from 0.1, 0.2, 3, 4. Okay, so as soon as you just go on increasing the voltage from 0 to 0, 0.1, 0.2, your depletion will become narrow and narrow and narrow. And when it reaches to 0.7, it is, I will just show you like this. Okay, for example, initially the depletion region will be like this. Okay, for example, if I say this is the PN junction diode, this is a P type material, this is N type material, and this is our depletion region D. Okay, so when the diode is forward bias like this, okay, so you have applied positive here and you have applied minus here. Okay, so what is happening here? Okay, the amount of charge will be flowing, and if you say that if you have applied 0.1 volt, what is happening? The diode is forward bias, but it is not conducting because the depletion layer thickness is large. So as soon as you go on increasing to 0.1, 0.2, 0.3, 0.3, okay, 0.4, what happens to this particular region? Okay, so this particular region will become completely go on narrowing. Okay, so it will be like this. So initially it was thick, now it becomes like this. So when you reach at a point that is nothing but 0.7, okay, so it will be completely like this. So what happens here? Your flow of charge will be like this. So the minority charge carriers and the majority charge carriers will start to move from one point to another, from P type to N type material, and then it will just make a complete loop, and then your flow, we say that yes, it is conducting. Okay, so this is how we try to work out with the depletion region, and as well as this is happening in the forward bias, but in case of reverse bias it is completely reversed. Okay, so as soon as you go on increasing the reverse voltage, your depletion region will go on getting thickness, or you can say that the depletion region will become thick. Okay, it will be like if I say that initially it is like this. Okay, so once you go on applying the voltage, it will start like this. Okay, so it becomes what happens here, as the thickness is getting increased with the increase in the reverse voltage, so the region width will also increase. So the amount of charge carriers from P and N type will not get exchanged. So what happens? The depletion region is thick, so no flow of charge or no flow of current will take place. Okay, so this is how under the forward bias and the reverse bias conditions will work. Okay, so when the depletion becomes narrow, then only charge will flow. Exactly how this is the what the thing is happening in the PN junction. So more narrow the depletion region, the amount of the amount of flow of charge will happen. And you know what, at some amount of time, for let us take 0.7 for a silicon diode, so you can also say that at 0.7 the depletion region breaks. The depletion region breaks. So at 0.7, okay, what happens here is nothing but there is no any junction at all. This is P and this is N. Let us say that at 0.6 you have like this. Okay, so what is happening at 0.7? I don't have any junction because you have broken the junction. So if there is no junction, what is happening? Then the flow of charge takes place. So this is how the whole PN junction will work out. Okay, so please remember how actually this is happening under the PN junction diode. Okay, how the diode is going to perform. Okay, so because this is what the basic thing is all about. Okay, so with this the normal VI characteristics with respect to the silicon and with respect to the germanium will occur. Okay, and if you look at this particular table over here, okay, the parameters to be observed when you just go on comparing forward voltage drop for silicon, actually it is 0.7, and for germanium it is 0.3. Okay, so normal reverse current is, it is very in few nanoamperes and few microamperes. So the breakdown voltages, it should be greater than 50 volt, and it is up to 100 volt. And what is the application of a diode? We use for the rectification and small signals, like when we go for detectors. Okay, so with this the normal VI characteristics of the diode, how this diode will perform under the reverse bias condition and under the forward bias condition takes place. Okay, so with this, I will just conclude my today's video lecture series of VI characteristics of diode. Okay, so in the next video lecture, okay, we will try to see with some particular equations. Okay, so what should be the amount of voltage? Practically, we will try to see how the actually the voltages are, how much voltage we require so that your diode will work out very properly, and some kind of applications related to a PN junction diode. Okay, and apart from that, there are some mathematical analysis to be done. Okay, and which are the parameters we need to consider, okay, under the forward bias and under the reverse bias. Okay, so with this, I will conclude my today's video lecture series on VI characteristics. Thank you.